Good afternoon to all of you. So, welcome back for the final session of this 2 days hands-on training on the NANODCAL and RESCU software. So, basically, in this session, you can do the hands-on practice of the device simulation. So, in this session, I will show you how you can create in your system any device and how you can do the simulation from the NANODCAL. So, based on the DFT plus NEGF method, you can simulate any device. So, you can see this is my C drive. And in this C drive, I have my device studio folder. So this is the device studio. I would like to open. And again, I would like to open this bin folder. Here you can see this is my device studio application file. So you can select this device studio application file. You can right click and you can run this device studio as an administrator. So you can run this device studio as an administrator. It will ask you to give the permission. Then you can select this yes. So here you can create a project. So you can start from the scratch. So create a new project. You can select this OK. And here you can enter the project name. So you can see this is my project name. You can choose the location where you want to save. Then select this save option. So that your project will be saved. So I hope everyone has been opened their device studio application file and they have created a new project. So here I would like to create a device structure and then I can simulate their various properties by using the NANODCAL software. So during this session, you can create the same device structure that I will show. Because whenever you increase the number of atoms, then the simulation time will be increased. So it is better during this session, create the same structure. And after this session, you can create your own structure. And then you can define their various parameters. And then you can do the simulation. So in this session, I would like to create a graphene nanoribbon device structure. So for creating a graphene nanoribbon device structure, we need to select this build option. And you need to select this graphene nanoribbon. So you can select this graphene nanoribbon so that you can create any nanoribbon. Either it could be graphene based, boron nitride based, MOS2 based, any nanoribbon you can create. So you can see this is the graphene nanoribbon. Here you can define the crawl vector, E and M value. And you can see this is the site A atom and site B. So in the site A, we have this carbon. In this site we have the carbon. So whenever you select this carbon, then it will make a graphene nanoribbon. So based on your research work, you can also create your own structure and then you can study their various properties. So here I would like to create a boron nitride based nanoribbon. So you can see this is the site A. You can double click on the carbon. Then the periodic table will be open. So from this periodic table, you can select this boron. You can see this boron has been selected. Then you can select this OK. So basically, I would like to create a boron nitride based nanoribbon and then I would like to study their various properties like density of state, transmission spectrum, IV curve, and various properties. So you need to select this boron first. Select this OK. Now you can see at this site A we have this boron. Similarly, we can change this site B atoms. We can double click on the carbon. From this periodic table, we can select this nitrogen. So once you selected the nitrogen, then you can select this OK. Then the carbon will be replaced by the nitrogen. Here you can see at the site B we have the nitrogen, site A we have the boron. Then it will make a boron nitride based nanoribbon. In the structure type you can see. This is the curl vector N and M. So you can take N is equal to 2 and M is equal to 2. So this information you need to select while creating any nano ribbon. First, you can change their site atom. You can also change their bond length. You can also passivate dangling bond with the hydrogen atom. You can also enter the curl vector and an M value. Then you can select this preview. You can change the site atom. Yes, you can change the site atom by double click on the atom. Then the periodic table will be open. And from this periodic table, you can select any element. Suppose we have the carbon, 1 second. So you can see this is the builder. This is the graphene nano ribbon. You can double click on this site A. And from this periodic table, you can select any element. Like for the boron nitride, we need to select this boron first. In the site B, we need to select the nitrogen. So you can double click on the yes.
That can you 3 elements at a time? Maximum more than 2 elements.
No, ma'am. You can select only any 2 elements in the site A and site B. But if you want to create any number of more number of atoms for the nano ribbon, here you can see we have the nanowire, nanotube builder, and in this nanotube builder you can create multiple structure, multiple atom you can select, and you can create their nanotube. But for the nano ribbon, you can select only 2 atoms. So after selecting this parameter, you can select this preview. You can see this is the boron nitride. So this is the boron nitride based nano ribbon. And this is the zigzag structure. So this is the zigzag boron nitride nano ribbon. So whenever you select this preview, then you can select this build option, so that your structure will be loaded in the device studio. So I hope everyone has been created this 2x2 boron nitride based nano ribbon. You can also rename this input file. You can select, right click, you can select this rename. Here you can change this graphene to boron nitride. So you can see this is the 2x2 boron nitride based nano ribbon. So once you created this nano ribbon, if you want to increase the length, you can select this build option. Select this redefine crystal. Here you can see this nano ribbon is quite thin. So if you want to increase the length, you can select this build option. Select this redefine crystal. So you can see this is the redefined crystal. By expressing the new cell vector UVW as a linear combination of A, B, and C. So in any direction you can create, generate, increase their length. Like this is the direction A, direction B, and direction C. So here I would like to increase the length in the transport direction, that is C. So C is the transport direction. And here I would like to increase the length. So you can see 5 times in the C direction. Then you can select this preview. So once you click on the preview, you can see the length of this nano ribbon has been increased 5 times in the transport direction. So you can increase the length 5 times in transport direction. Select this preview. Then you can click on this build option. So you can see this is the 2x2 boron nitride nano ribbon. This is the 2x2 boron nitride redefined nano ribbon. In this structure, we have increased the length in the transport direction. You can also measure the distance of this nano ribbon. Here you can see, this is the distance measurement. So if you want to measure the distance, you can see this is the distance measurement. You need to select the atom. So 2 atoms you can select, then you can measure the distance. So once you increase the number of the atom, then you can go to this convert to device option so that you can create this structure into device. So if you want to convert this structure into device, here you can see, this is the convert to device. You can select, then you need to define their electrode. So this software support 6 probe device, like you can define the left electrode, right electrode, bottom electrode, top electrode, front electrode, and back electrode. So up to 6 probe device structure you can easily simulate from the NANODCAL software.
Sorry, sir. May you repeat again?
So this NANODCAL can support 6 probe device structure. Like you can define the left electrode, right electrode, bottom electrode, top electrode, front electrode, and back electrode. So based on your device structure, you need to select the electrode. But it is also possible to create any electrode. Here you can see this is the left electrode and this is the right electrode. Here you can see we can't select this bottom and top because we don't have any atom on the bottom and top side. So here we can select only 2 electrode, left and right, then select this preview. Now you can see this is my left electrode, right electrode, this is my center region. So this is the center region, left electrode and right electrode. Now you can see 2 electrode has been selected. Select preview, then select this field option. Here you can see this is our 2 probe device structure where we have the left electrode, right electrode, and center region. So center region is also called the scattering transport region. Now you can see this is our device structure. Here you can see this is the 3D viewer. You can show their XY view, XZ view, YZ view, YX view, and ZX view. Like you can see this is the ZX view where we have this left electrode, right electrode. So these are the left electrode, right electrode, and this is the center region. In this device structure, you can see total number of atom is 40. So 40 atom we have in this device structure. This is the vector value, vector A, vector B, vector C. This is the vector value for the left electrode, right electrode, and this is the total, this is the center area of this lattice. So you can see I have created a simple boron nitride based nano ribbon device structure. And this is the 2 probe device structure. In 2 probe device structure, we have the left electrode, right electrode, and center region. You can also define the 3 probe device structure so that we need to convert this structure into transistor. Like we can define their drain, their source, and their gate term. So I hope everyone has been created this device structure. And now we can move on the simulation. So for simulating any device structure, we need to select the simulator. We need to select this NANODCAL because the device simulation is not possible from the RESCU software. So you can simulate the device by using NANODCAL based on the density function theory. plus non-equilibrium green function theory. So DFT plus NEGF will apply in the center region and DFT will apply in the electrode part.
What's add buffer? Add buffer.
So if you want to add the buffer, like a buffer is for the, here you can see, this is for the left region and for the right region. So if you want to increase the number of atom, then you can use the buffer, either left side and right side. You can see.
Is it similar to supercell?
No, it is not similar for the supercell. Supercell you can create from this redefined crystal.
Could you repeat, please, just for 1 minute before, because my it was not visible.
So which like a add buffer option or something different? Like for simulating any device structure, we need to select the simulator. Select this NANODCAL. Then we need to define the DFT plus NEGF parameter by using this self-consistent field calculation. So for device simulation, you need to select this NANODCAL. Then you can select this CHCF calculation. So once you selected this CHCF calculation, here you can see, this is the self-consistent field calculation for the device. And here you can see these are the parameters that we need to define. Like we can change their electron temperature, their cutoff energy, their exchange correlation function, LDA, GGA. We can also change the K-point sampling. We can also define the contour integral. And then we can go for the electrode. You can see these are the electrode parameter for the left electrode and for the right electrode. So you can see, I would like to define here 0.1 voltage at the left electrode and here I would like to define minus 0.1 voltage at the right electrode. But you can also define your own parameter. So you can see this is the left electrode parameter and this is the right electrode parameter. This is the iteration control. So every parameter you need to define. You can see this is the basic setting. This is the Spintronics application. In the Spintronics, we have the collinear spin and general spin. You can take this noise spin. So once you define the parameter, so after defining all the parameter, you can select this generate file. You can click on this generate file. Then your input file for the left electrode, right electrode, and device will be generated. So once you define the parameter, you can select this generate file. And here you can see the input file for the left electrode, right electrode, and device has been generated. So these are the input file. So there is no need to write any script for any structure. You can simply create the structure. You can define their various parameter. You can define the DFT parameter, DFPT parameter, NEGF parameter, and then you can generate their input file. So this graphical user interface is very easy to use. So if we talk about their script for the left electrode, right electrode, and device, you can see this is the scf.input file for the left electrode. You can select this file, right click. You can select this open with. And you can see this is the script for this 2 probe device structure. And this is the script for the left electrode. You can see this is the SCF calculation. This is the basic setting. Here you can see no spin is included. This is the iteration control parameter. These are the atom and their Cartesian coordinate point. Here you can see we have total 8 atoms in the left electrode. You can also change any input from this script mode. You want to change here, you can see. You can change the value like that. And then you need to save this input file. So either you can change the value from the user interface, and either you can change the value from this sf.input file script mode. Now we need to run the input files. So we need to run the sf.input file for the left electrode first. Then we can go to right electrode. And then we can simulate this sf.input file for the device. Because this sf.input file will take the output from the left electrode and right electrode. So before simulating this is sf.input file, we need to simulate these are the input file for the left electrode and right electrode. So you can select this input file, right click. You can select the run option. Here you can select this run option to run this job. Now you can see our left electrode SCF input file is in the running condition. Similarly, we need to run right electrode input file. So you can see this is the right electrode input file. We need to run. Then we can select this sf.input file of the device. We also need to run this input file. So in the job manager, you will find our scf.input file for the left electrode, right electrode, and device. You can see the scf.input file of the left electrode is in the running condition. So in the queue condition, you can run multiple input file. And once this simulation will finish, then this simulation will start automatically. So multiple input file you can run in the queue condition. So once you run the scf.input file, then you can go to the analysis. So after running this input file, you can select the simulator. Again, you can select a NANODCAL. Then you can select this analysis.
Sir, what is the relax and transistors?
So relax is basically for optimizing the structure. Like if you want to optimize this device structure, then you can select this relax. Here you can see these are the parameters that you can define. You can see, you can select the EMD, that is for the molecular dynamic, and CG is for the conjugate gradient. So these two methods you can apply for optimizing any structure. So relax is basically for optimizing the structure. And if we talk about this transistor, so you can see this is the transistor, so that you can make a 3-probe device structure. Like if you want to create a MOSFET transistor, so from this transistor option you can create. You can see this is the gate parameter, where we have this spatial region. Like we can define the dielectric permittivity, we can define the thickness of the oxide layer, and then we can define the gate. Here you can see we can define the gate voltage, we can define the gate region, we can define the source and drain. Like here you can see, I would like to define 5 angstrom thickness. You can see this is the oxide layer, this is our drain, this is our source, and here we have the gate. So this is the source, this is the drain, and this is the gate terminal. Also you can change the source. Here you can see this source is located at the right side. We can change this source at the right, left side. You can see this is the source, this is the drain, and this is the gate. You can also apply the biasing voltage. You can also apply the gate voltage. Gate region you can also change. Like here you can see, if you want to change, now you can see. So for creating a transistor, we can go simulator, select the transistor option. So that when you can select this transistor option, it will also generate the SCF.input file and IVcurve.input file. And whenever you do the simulation, then you can plot their IDBD characteristics, IGBG characteristics. Now you can go to the analysis part for this device. So you can select this simulator. You can select NANODCAL. And here you can see this is the analysis. Now you can see this is the analysis for the device structure. So various property you can analysis for the device, for any device structure. You can see this is the density of state for the device, and this is the density of state parameter. Here we can define some key point sampling so that we can plot the density of state. Like here you can see, I would like to take 5. So N1, N2, N3 is equal to 5. So you can see I have selected N1 is equal to, N2 is equal to, N3 is equal to 5. This is the number of energy points. This is the energy range, and this is the projection. So this is the density of state. We can select the transmission spectrum. You can see this is the transmission, and these are the parameter, K point sampling, number of energy point, and energy range. You can select this IV curve. Here you can see we can define their K point sampling. You can select this electron density. Again, you can select this potential. So multiple input file you can select. Like this is the thermoelectric current. This is the Seebeck coefficient. So you can see this is the density of state and their parameter. I have defined n1 is equal to 5, n2 is equal to 5, and n3 is equal to 5. This is the transmission spectrum. I have taken the default parameter. This is the IV curve. This is the electron density. Here you can see. This is the charge density, total electron density. So multiple density are available. This is the potential. You can see effective potential, Hartree potential, exchange correlation, and neutral atom. So if you want to calculate the Coulomb potential, then you can select this Hartree. This is the thermoelectric current. You can see this is the K-point sampling. And this is the temperature. Here you can see this is the Seebeck coefficient. So whenever you define the parameter, then you can select this generate file so that their input file will be generated. Now you can see this is a generate file and the input file has been generated. Here you can see the left electrode input file has been completed. The right electrode SF.input file has been completed. And now this SF.input file of the device is in the running condition. So similarly, you need to run all this analysis input file in the queue condition. Like you can see, this is the density of state. This is the transmission. This is the IV curve. This is the electron density. This is the potential. This is the thermoelectric current. This is the Seebeck coefficient. So in the job manager, you can see I have run all this analysis input file in the queue condition. So this device simulation will take some time to simulate the structure. Here you can see, if you want to show the step-wise step procedure of the simulation, you can open the log file. You can see this is the log file for the device. This is the log file of this left electrode, and this is the log file for the right electrode. So in the log file, you will find all the step-wise step procedure, and also you will find the simulation time. Like here you can see, this is the electrode SF.input file, and this is the log file. You can select this log file, and you can select as open with. You can see this is the SF calculation. It has loaded the pseudopotential file of the nitrogen and for the boron. You can see this is the periodic device structure where no spin is included. And here you can see this is the step-wise step procedure. You can see this is the time, this is the raw matrix, hybrid matrix, total energy, band energy, grid charge, and orbital charge. So it has taken 28 iterations. Here you can see this simulation has been completed, and it has taken total 2 minutes 12 seconds for the left electrode. So in the same way, you can select this right electrode log file, and you can see it has taken 2 minutes 17 seconds. And now you can see the device sf.input file is in the running condition. So whenever the simulation will be completed, then you will get the output file. So in the same way, you can create any device structure, and you can do the simulation with the help of NANODCAL. So in the toolbar, you can see this is the distance measurement, this is the angle measurement, this is the dihedral angle measurement, and this is the vector measurement. Suppose if you want to measure the angle or distance, like you can see, this distance measurement has been selected. You need to select any two atom. Then it will measure the distance between these two atoms. You can see 2.460 angstrom. So this is the distance measurement. Also, you can measure the angle. Here you can see this is the angle measurement. You need to select any three atom. Like you can see, this atom, this three atom has been selected, and the angle between these three atom are 60 degree. So this is the distance measurement. This is the angle measurement. And here you can see, this is the dihedral angle measurement. Like if you want to measure the angle between four atoms, then you can select this dihedral angle measurement. Like if you want to measure the angle between four atoms, like this atom, this atom, this atom, and this atom, you can see. So any four atom you can select so that you can measure the dihedral angle. And you can see this is the vector measurement. Like if you want to measure the vector between two atoms, you can select this vector measurement. And you can select any two atom. You can see this is the vector value. And for the theory and background simulation, you can visit our official website. This nanoacademy.com you can visit. Here you can see this is the document and tutorial. You can see this Nanoacademy technology has developed this product like NANODCAL, that is for the atomistic quantum transport simulator based on the DFT plus NEGF method, so that you can simulate any material and any device structure. This is the NANODCAL plus. So this is the advanced version of this NANODCAL that is written in Python. And this NANODCAL is written in MATLAB and C. So you can see this is the RESCU software. So this is for the large scale atomic simulation. So you can simulate any material, complex material, hexagonal, tetragonal. So any material you can simulate with DFT and density function perturbation theory. You can see this is the RESCU plus software. That is the advanced version of this RESCU. Like this RESCU is written in MATLAB and C, and this RESCU Plus is written in Python and Fortran. Also, we have this QTCAD software. That is basically a TCAD software based on the FEM method, so that you can simulate the spin qubit in the semiconductor. So these are the various products that Nano Academy Technology developed. So you can select any product.
TCAD.
So you can see this is the ticket. So basically this, yes.
This is for what purpose? Using for what purpose? TCAD.
So basically for the spin qubit devices in semiconductor. So qubit simulator for the quantum technology you can simulate. You can see this is the getting started. So basically you can see this QTCAD is a finite element based simulation platform for the quantum technology that is developed by Nano Academy Technology. And this QTCAD has an electrostatic tool that can solve the confining potential of the quantum dot in the semiconductor nanostructure, so that you can find the corresponding envelope function for the electrons and holes. They also have a valley splitting tools for the valley coupling of the nanostructure. They also have this exact diagonalization tool for the rigorous treatment of the Coulomb interaction between the few electron system. Also, they have the master equation solver for the quantum transport calculation in the sequential tunneling regime, so that you can enable the treatment of Coulomb blockage and you can calculate the charge stability diagram. So they also have the electric potential spin resonance module that will interface with the QT for the time-dependent simulation of the quantum control. And you can simulate any device structure at the cryogenic temperature for the solid state spin qubit. So this QTCAD comes with the Python interface. So a very user-friendly Python interface, so that you can define their various parameters. You can also define the material like their doping density. And also they have this compatibility with the device. So basically this device Gen is a open source coding software where this Nano Academy Technology developed. So this Nano Academy Technology also developed this device Gen. And also it enables the integration with the GMS, so that you can generate a 3D geometry file from the GMS. That is also open source software, meshing software. So this QTCAD comes with the three simulator, like they have the device simulator, qubit simulator, and transport simulator. So device properties, transport property, and qubit property you can simulate from the QTCAD software. Here you can see some tutorial are mentioned. Like you can see Poisson and Schrodinger simulation of the gate all around field effect transistor. So this is the device simulator. Also they have this transport simulator and they have the qubit simulator. So qubit properties, transport properties, and device property you can simulate. So you can see. So you can see this is my Visual Studio interface. That is a graphical user interface of the Python. And here you can see I have written various commands for various structure. You can see this is the gate all around field effect transistor, and this is the input file. So this is the Python input file. So you can see I have imported this CT, that is basically universal physical constant. I have defined the mesh. I have also defined the input and output. I have also defined the analysis parameter, and this is the material. Here you can see I have imported this Poisson solver. Also imported this Schrodinger solver. You can see we have defined the device parameter, their gate to source voltage, their metallic work function, total length of the device, and this is the radius. You can see this is the path for the mesh file. We need to load the mesh file first. Here you can see in this device we have defined the FD approximation. That is basically for the analytical approximation to the Fermi direct statics. Here you can see in the channel oxide layer we have defined the material silicon dioxide. This is the source oxide layer. This is the drain oxide layer. And we have the channel source and drain. In the channel source and drain we have the silicon. Also we have defined the doping. You can see I have defined the boundary condition like ohmic boundary condition at the source, ohmic boundary condition at the drain, and gate. You can see this is the gate boundary condition. You can see I have defined the nonlinear Poisson solver. So this is the nonlinear Poisson solver. And you can see these are the various properties that I want to simulate. Like you can see this is the electron density, hole density, phi, charge, electronic charge for the conduction band and valence band. So with the help of this nonlinear Poisson solver, we can calculate the electric potential, and with the help of Schrodinger solver, we can calculate the envelope function. Like you can see, we can calculate the ground state, first excited state, and second excited state. Here you can see I would like to run this input file. So first it will load the, you can see this, it will first load the Gmesh. So there is a license issue. So for the theory and background, you can visit this nanoacademy.com. Then you can go to the documentation and tutorial. And here you can see this is the NANODCAL. So whenever you go to this website, then you will be more familiar about the product, NANODCAL, RESCU, and QTCAD. So you can see this is the QTCAD software, and this is the NANODCAL. So here you can see we have the theory. You can see this is the basic introduction. So this is the basic introduction of this NANODCAL. Like here you can see this is the left electrode, right electrode, and this is the center region. So center region is also called the scattering transport region. And you can see this is the density function theory in the NANODCAL. Here you can see these are the various equations and their theory are mentioned. Like you can see this is the flowchart of the self-consistent cycle in a standard DFT calculation. Also you can see this is the linear combination of atomic orbital basic function. So this is the DFT in the NANODCAL, and also you can see DFT plus NEGF in the NANODCAL. You can see this is the left electrode. This is the gold based, electrode. Here you can see this is the biphenyl molecular structure, and this is the right gold electrode. So you can see this is the flowchart for the self-consistent cycle in the DFT plus NEGF calculation. So whenever you get the time, you can visit. And for the input reference, you can see this is the input reference. And here you can select this calculator parameter. So for calculating particular analysis input file, what parameter you should set, like you can see, these are the various calculation band structure, primitive cell vector. This is the symmetry K point. Here you can see. This for the band structure calculation, 0D dimensional G, X for the 1D dimensional, GMKG for the 2D hexagonal. So here you can see the sf.input file of the device has been completed. And if we talk about the timing, so you can open this log file. You can see it has taken 22 minutes 49 seconds to simulate this CSF.input file of the device, because it has taken the output from the left electrode and right electrode. And now you can see our device density of state for the device is simulating with the help of green function method. So you can wait till the simulation. So once the simulation completed, you will get the output. Now you can see the density of simulation has been simulated and their output file has been generated. Here you can see this is the density of state that has been completed and their output has been generated. Here you can see this is the density of state plot for the 2x2 boron nitride waste nanoribbon device structure. You can see this is the number of state per electron volt and this is the energy range. So this is the density of state plot. You can also export this raw data in any format. You can see this is the export option. Here you can select the format. Either you can select PNG, JPG, BMP, PDF, text. So any format you can select. Like you can see this is the JPG. Then you can select the save option. So where you want to select, you can select the location. Then you can click on the save option so that you can easily export your raw data in any format. You can see I have exported this data in the JPG format. So this is my density of state. And now you can see the transmission spectrum is in the running condition. So you can see this is my contact number. So for any future requirement, any technical support, you can let me know so that we are ready to help you. Either you can drop the mail, either you can contact through this given number. You can also send me the WhatsApp. So as you know, the validity of the license is for the 2 months. So you can evaluate our software properly. And for any help, any technical help, you can let me know so that I will ready to help you. And after this session, you can also create your own structure. Also, you can define your own parameter. Then you can do the simulation. And if anyone facing any problem while downloading the software, either their license is not working, either creating any structure, then kindly let us know so that we are ready to help you. You can see the transmission spectrum is in the running condition. So now if you have any query regarding any simulation, either it could be material simulation, device simulation, so you can unmute and ask me the queries. So whatever the query you have, you can ask. And also you can visit our YouTube channel. You can see this is our YouTube channel, Impulse Technology, Innovative Research. Here you can see we have the playlist of the software. Like you can see, this is the QT cat for the quantum technology spin qubit device. This is the RESCU software that is for the large scale material simulation. Also we have the Laos. Also we have the SETFOS that is for the optoelectronics application like thin film, solar cell, OLED. Then we have the SETFOS software. You can see this is the NANODCAL software. So you can open the playlist, then you will find various video for various application. So this is the NANODCAL playlist. And here you can see, this is the RESCU playlist. So you can see, this is the 2 probe device structure. I suppose if you want to create a 4 probe device structure. So for the 3 probe, you can select this transistor. And for the 4 probe, you need to create the structure first so that you can create the structure. Like you can define some atom in the top, bottom, left and right so that you can create the 4 probe. Like suppose if you want to create a 4 probe.
Sir, excuse me, sir.
Yes, sir.
So we can create a layering in this structure.
Yes, sir.
The
Layer structure you
first
can,
layer,
like you
sir,
can see. Yes.
sir, like that, sir. First structure, first layer is there, and we can create bottom layer or uppermost or two more layer can be add in this.
Yes, you can add multiple layer structure you can add. Like if you want to add one more layer, either the same structure you can create, either different structure you can add. Like if you want to create a same layer, you can select, like you can select this atom, then go to this mirror atom. Here you can define the normal vector. You can define the distance between the layer. You can copy this checkbox. This you can click on this apply. Now you can see this is our second layer. You can also change the material. Like if you want to change this material with another atom, from this replace atom, you can change. Like you can see, this is the graphene nanoribbon and this is the boron nitride nanoribbon.
Yes, sir.
So multiple layer structure you can create. So there is no limitation of layer. And suppose if you want to create a 4 probe device structure, like here you can see, I would like to create a 4 probe. So first you can design your structure. Like you can see, this is my desired device structure. So there is no atom, so we can remove. So whenever you design the device structure properly, then you can select the electrode. Like if you want to convert this structure into 4-pro, like here you can see, we can define left electrode, right electrode, bottom electrode, and top electrode. So whenever you design the device structure properly, then you can create their electrode. So it will take some time to simulate this structure because it is having total 40 atoms. Now you can see transmission spectrum is running. And also we have given you the evaluation license. so that you can run the job on serial core. So only one core you can utilize at a time. But whenever the user purchase our software, then we will provide them the cluster license so that they can run the job on parallel. Suppose 5 core, 10 core, 16 core. So parallel simulation will be possible after purchasing the software. Then your time will also decrease.
Can you show me the IV curve graph, sir?
Now you can see simulation is running. When the simulation completed, then we can get the IV curve.
Okay, sir.
Here you can see, I have created some project earlier and I have simulated their IV curve. Like you can see, the same structure I have created for the 2x2 graphene nano ribbon. So this is the graphene nano ribbon. Here you can see, I have simulated with different biasing voltage. And here you can see, we have simulated the result input file. And after the simulation completed, we will get the output file. Like this is the current voltage curve.mat file. And also we can get the current voltage curve.xml file. So this mat file you can double click, then it will be selected. Here you can see this file has been selected. You can type data. And you can press the enter. So you can see we have defined 0.4 biasing voltage and we get the current value. So this is the I2 1.7970 into 10 to the power minus 5. So whenever you get the result from the simulation, then you can select this new script. Like you can write some command, you can enter the value of voltage, you can enter the value of current, you can write some command so that you can get the plot. Like you can see this command you need to write. You can see I have defined the voltage 0, 0.2, 0.4, 0.6 and 1.0. This is the V2. This is the I1 total current. In this structure, I have defined the spin. It's Spintronics application like collinear spin. So that is the reason I get two output for the current. First one is for the spin up. Second one is for the spin down. This is the I2 total current. This is the I2 spin up. This is the I2 spin down. And you can see this is the command that will plot your data. Like V1, I1. And also you can see this is the x-axis. I have defined the voltage. And the y-axis, I have defined the current. And this is the title of this graph. The graph between the current and voltage. And once you write this command, you can select this run option. Then you will get the plot. You can see. This is the spin current of the zigzag graphene nano ribbon. You can see. You can see the same structure I have simulated. You can see this is the transmission coefficient for the antiferromagnetic, for the ferromagnetic. And you can see this is the spin current. You can see the same graph I have plotted here.
Sir, how did you select the FM and AF in NANODCAL?
Like here you can see. So this is the zigzag graphene nanoribbon. And here we have studied the zigzag graphene nanoribbon for the ferromagnetic and antiferromagnet configuration. You can see the zigzag graphene nanoribbon has been predicted to the half metallic, ferromagnetic and antiferromagnetic with the magnetic moment at the edge side. So at the edge you can see we have the hydrogen element, and in the spin polarization we have defined the magnetic, so that it will be ferromagnetic. You can see, or zigzag graphene nanoribbon ferromagnetic. In the input file you can see this is the spin polarization. So whenever you define a spin polarization, then first it will become a ferromagnetic, and whenever define 0, then this structure will act as an antiferromagnetic. You can also download this input file. Here you can see these are the Cartesian coordinate point, and this is the spin polarization. So here you can see so this is the spin polarization. So whenever you select here either 1, 0, then it will become ferromagnetic and antiferromagnetic. So for the Spintronics application and their parameter, you can visit this website. This is spin polarized calculation. And also you can visit this tutorial page. Here you can see the transmission spectrum has been simulated. You can see this is the graph. So this is the transmission spectrum for this 2x2 boron nitride nanoribbon device structure. Here you can see this is the transmission coefficient and this is the energy.
Sir, can we apply spin orbiting coupling SOC?
Yes, SOC you can also apply it. You can enable this spin orbital interaction, then your SOC will be applied.
Okay. If it is 1, 1, it will be paramagnetic. Now, means rho is equal to 1. 1 means paramagnetic.
You can visit this spin polarization, then you will get more familiar. Like what parameter 1, 0, either -1, something that you can define. You can visit out this one.
Okay, okay. Thank you.
So you can see this is the transmission spectrum with respect to energy that has been simulated. This is the current voltage curve, and this file will open in the MATLAB. So their MAT file you can open in the MATLAB. So this MAT file you can open in MATLAB. Here you can see this is the total electron density. So you can see this is the 3D view. This is the 2D view along x-axis, y-axis, and z-axis. You can see this is the planar display. This is the stereoscopic display. And this is the 1D view along xy plane, yz plane, and xz plane. You can see this is the Coulomb potential. So this is the 3D view. This is the 2D along x-axis, y-axis, and z-axis. This is the planar display, stereoscopic display. And this is the 1D view. If we talk about this current voltage and thermoelectric current, so I can open this file into MATLAB. So you can see this is my device studio. So this is my device, 2x2 boron nitride nano ribbon device structure. Here you can see this is the device folder. Here you can see we have the current voltage curve.mat file. Here you can type command data, then you will find the output. You can see this is the voltage V1, 0.1. This is the current I1, 2.7696699 into 10 to the power minus 5. This is the V2, minus 0.1. And this is the current I2, minus 2.7699 into 10 to the power minus 5. So you can see I have run at a single point, like I have defined the voltage for the left electrode 0.1, and for the right electrode I have defined the minus 0.1. So whenever you define multiple voltage, either you can define the range, then you will be able to get the plot. So this is the single point data. Also, you can see this is the thermoelectric current.mat file. You can see this is the applied voltage and this is the thermoelectric current. You can see this is the applied temperature. If you want to show this thermoelectric current, here you can type data dot thermoelectric current, press the enter. So this is the IV curve plot, thermoelectric plot, and also you can see this is the photocurrent plot. Here you can see this is the photocurrent plot. So photocurrent is also possible. So I hope in 2 days hands-on training, you learn how to simulate any material, any device by using density function theory, density function perturbation theory, and NEGF theory from the NANODCAL and RESCU software. So you can also create your own structure and you can do the simulation. Yes, sir, definitely. We can provide you the recording video after this workshop. So from my side, thank you so much to all of you for your registering here regarding the 2 days hands-on training on the NANODCAL and RESCU software. So for any technical support, any requirement, please let us know so that we are ready to help you.